So we come to the statistics of parameter estimation now. So as we have seen previously, one has to make several measurements from the statistics. Uh, and from these statistics, one infers the parameters. So as you can already guess, one need to use some sort of a statistical estimation or data analysis. So really, in the parlance of statistical estimator, an estimator, mathematically it's just a function. I just name it as Y, estimator, which is essentially a function that will take all your measurements and then it generates an estimate y_est of the parameter x, based upon, of course, based on the data. Remember, this was our measurement record. So now the question arises, how well do n measurements determine the parameter x? Remember, x in our case, in the example we just saw in case of quantum metrology, was the frequency omega. So one way to benchmark how well our measurement process is doing, the obvious candidate is just the variance. Variance of this guy. So the variance captures how well one is doing in parameter estimation. I'll just give you an example. So for example, let's say this is the x-axis, which would contain the value of the parameter, which is to be estimated. So, and I'll just say that, let's say in actuality this was the value of the parameter. And we perform a series of measurements, and sometimes these are the statistics. I get some, at every run of the experiment I get different M1, M2, so on and so forth, Mn. I get various values of the measurement record. And for the sake of simplicity, let's say roughly it turns out to be a Gaussian. So, in a sense that my estimate is a random variable, a random Gaussian variable, for example. So, so this was my estimates, or this is the histogram of the measurements. So in other words, your estimate x est, the estimate of the parameter x is a random variable. Well, this can happen. For example, you're measuring a length. In one go, you measure the measurement records of, let's say you're trying to measure a stick, which is in reality 5 meters. You might measure it 5.02, 5.02, 4.99, and these are all your essentially measurement records. And what we are assuming is that that measurement record is clustered around the actual value of the parameter as a Gaussian variable. So one of the ways to see or benchmark the quality of my estimation process is essentially calculating the obvious candidate, so to speak, is what we've already mentioned. I'll just write it down again. The variance. This guy. Now, for example, let's say I have two parameter estimation schemes. This is the x-axis again, and I had a parameter embedded which needs to be measured. So in the first case, I make my measurements clustered around here, so on and so forth, and this is how my random variable or my measurement record, the histogram of the measurement record, looks like. Let me call it experiment 1. In the second case, I have a really good measurement record and all the values of the measurement record are clustered around a very narrow Gaussian random variable. So intuitively you can say that the experiment 2 is better because statistically speaking, this data gives us a better estimate of the parameter. And it sort of makes sense. So hence, again writing the same thing, we say that the variance is a benchmark of our metrology process. The more the narrow the variance of this probability distribution of the measurement record, the better we are doing. But if you look at carefully, this quantity, the variance of the estimator, this has two issues, two very minor issues, but it's sort of important to go through it. It has two issues. You could have already guessed what are the two issues. One is that my estimate can be systematically biased away from the two parameter value. So I'll just write it down. Even if the estimation has a small variance, it can be systematically biased away from the true parameter. So in other words, the mean value of the estimate might not even equal to the parameter. For example, I have a parameter which I was about to measure over here, and suppose my dials or my spring is offset. It's a very good estimator, it's a very good experiment, but it's just offset by some default value. So all the data what I get, even though it's narrow, it's clustered around some offset value from the actual value of the parameter. So we need to fix that. It's a really simple fix. The other thing we need to fix is that the estimator might have different units from the actual parameter that one needs to measure. So therefore this makes it difficult to interpret the variance of the estimator. So it just boils down to a question of change in units. So for example, this can happen when our measured quantities M1, M2, Mn have different units. They are related to the parameter we are measuring, but they have different units, so to speak. So for example, let's say in our spring mass system example, what was required? We were required to essentially measure the mass. So in our example of the spring mass system, we were measuring the mass was to be measured, but the way we were measuring M was through the elongation of the spring. We did this many times, and from this quantity, the length of the extension of the spring, we were inferring the value of the mass. So an estimator based upon this needs to give us information about the mass. So we need to change the units. It's a simple point. So for example, let's say mass to be measured was proportional to the length of extension M, or M was equals to lambda L. We need to extract the scaling factor in order to be able to put it and put it back to make sense of the variance of our estimation. And really what the quantity that does it is the derivative. So this sort of a derivative is going to take care of the lambda factor, or the units of my estimation process. So this is just a scaling thing. The random variable M estimate which you are going to get will be dependent upon L, L is related to the actual mass to be measured by lambda. So all my variances might be scaled by some factor which I need to take into account, and this derivative takes precisely uh, uh, into account that my estimator, the function which I am which takes inputs as my measurement record, might have different units, or I might be measuring a different quantity in order to extract information about the parameter. So combining 1 and 2, I have the remedy. The remedy is I, instead of examining the statistical properties of the random variable y estimate, I define a rescaled y estimate. This is just my derivative, which takes into account the units, and I subtract it with the actual value of the parameter. So this thing takes into account the offset, and this factor takes into account that my estimate y est might have different units than the parameter I need to measure. So this quantity, another random variable, if I study the properties and the variance of this particular quantity, that's going to tell me about the quality of my metrology or my experiment, taking into account everything. So what do I do now? So now I'll be interested in the variance of this quantity instead of my original variance of y estimate, and this is going to tell me a way to benchmark how well we have carried out the estimation process. So let's say I have to compare two metrology schemes, one metrology scheme with another, one experiment with another. I'll have to calculate the variance of this particular quantity, which is the variance of the rescaled estimator fixed for an offset bias, and this quantity is going to tell me how well I am doing in my metrology protocol.